I hope my screen would be visible. So, this was discussed in last lecture. We discussed two things. Initially, we discussed what are the switching functions and how it will be helpful when we try to find higher order ripples or harmonics in other power electronics converters. Later on, we got into interleaved converters, where we saw if we connect parallel converters, then what happens? Our ripples get reduced, or in some cases, it will be almost zero. Like we saw that problem which was asked in 2018. So when we sum up both the signal of inductor current, what happened in the end? That inductor current becomes zero. And one or two very interesting observations we can see from here, like how much phase shift we should do and how many parallel converters we can connect, right? Uh, we connected two, we can connect four, we can connect six also. So, what are the benefits and what are the cons in that? So, those observations we will see. And further on, did anyone try with phase shift of 90-degree? In any case, this was the circuit here, and I told you to just go and see what happens when you give the phase shift of 90-degree instead of 180-degree. In case of 180-degree, our ripple was zero, but in case of pi by 2, something else is happening, and why that? So, even I gave some hint that this signal would look like that, whatever it is here. Okay. So, okay, so I don't think anyone tried that. No worry. Even so, two important observations was first of all, since ripple was getting zero, so we do not observe what are the frequency of that interleaved converter ripple current. So that was very important, and we will see some finite ripple even after connecting multi-phase. Then we can easily understand. And second thing, how many converters we can connect in parallel. Okay. So before that, we saw these things. These are the ripple in capacitor voltage. These are the ripples in inductor currents. And further on, we solved two problems based on boost converter and one based on interleaved buck converter. So moving ahead in today's class, yeah, so if you can observe this circuit, so this circuit is nothing but just the interleaved boost converter. Okay, so here both the inverters are, or sorry, both inductors are connected directly to the source, and here one main switch which we can control or which we have control on, and another uncontrolled diode is present, and both the converter supplying to a common load. This is the common load. Okay, and for convenience I have drawn the uh, current in inductors in each inductor. So let us assume this duty cycle is 0.35. At any point, if you are not able to get it, just interrupt. Okay, so let us assume duty ratio is 0.35, and it is getting charged for that period and getting discharged for another 0.65 of duty cycle, right? And in complementary fashion, this switch H2 is in complementary fashion of H1. Okay, if you connect any NOT gate, it will do the work. And when we are adding both the signals, this kind of pattern is coming. Okay, so even after connecting two parallel converters, there will be some ripple, because we have limitation on the size of inductor, we have limitation on size of capacitors, right? So now I will take a reference from a book named Daniel Hart. They have drawn this kind of ripples, right? So here,
Yes, sir.
uh, so here what was happening earlier, IL1 was increasing and IL2 was decreasing. Okay, after getting summed up, okay, after getting summed up, during the period IL1 is increasing, the sum is increasing. Why so? Because here duty is less than zero point 0.5. That is another scenarios where duty ratio is less than zero point 0.5 or is less than 0.25 or greater than 0.25. So here duty ratio is greater than 0.25 and less than zero point 0.5. So in this scenario, your rising slope would be lesser. Okay, rising slope here it is lesser than the falling slope. Okay, why it is happening we will discuss, but for time being, see here the frequency of individual inductor current, you can see that is nothing but the switching frequency, right?
Yes, sir.
Is nothing but the switching frequency. But after doing interleaved connection, what is the switching frequency you can observe in the ripple, total ripple current?
Uh, Two times.
Yeah, correct. Very good. Two times. It is nothing but the two times of frequency. And this value, if you compare with this value, this ripple value will be always less than this ripple. And that will depend on your duty cycle and the value of peak to peak current. Okay, it will not be always, half of that in as we saw in last case. It will be certainly less than this peak to peak. Let's say del IL1 and del IL2. So in any case, del IL2 will be less than del IL1. Okay. How much less? That will again depend on inductor size, again on the duty cycle. Okay. So this thing are very interesting to visualize here. And in other case, let us suppose D is duty ratio is less than 0.25, then you will see that rising slope would be higher than the falling slope. Now you can draw on yourself and you can visualize this criteria. What will happen if duty ratio is less than 0.25? These are very small exercises, but if you do on your own, you will get better insight than rather than just listening here. But anyway, so these are the things you can keep in mind. And further, what I wanted to discuss, yeah. So what we will do, we will see some problem here, and after that we will see what happens in discontinuous conduction mode. So I hope in interleaved converters, either buck or boost, if you have any problem, you can ask me, because I don't think after this point I will be discussing any more this interleaved converters. So any point you felt like this is not clear, you just ask me. And one more thing, like how many converters you can connect in parallel. So the general rule of thumb is you can connect any number of converters. That is no issue. But how much is generally considered as efficient? So how much ripple frequency of inductor? Inductor will have some impedance, and that will act as a filter also. So whatever the size of inductor you have in your hand, if you multiply this number of converters into frequency, that that much circuit you can connect. And those phase shift, let us suppose you have three converters, three interleaved, then how much phase shift will be given to individual converters, right? So here two converters was connected in interleaved connection. So phase shift was 360 by 2.
180.
Yeah, correct. 180. If you connect three, then what will be the phase shift? Simple mathematics. Yeah. So 120 in case of three. So in that manner, and the more number of converters you will add, the less ripple you will get with limited value of inductance, right? So that was the point I wanted to discuss here. So okay then. So I think that is it. Um, First, we will solve one simple problem based on buck converter, and then we will see the same problem with the effect of discontinuity in inductor current. Okay. So for time being, uh, these are the values of buck converters. Let me show the image of buck converter also. So this is buck converter, a typical buck converter, and these are the values here. Let me call it question number one. This question you can easily find in that book I mentioned, that Daniel Hart. So there will be two instances. One will be turn on and other will be turn off. Okay. So here you need to find out the output voltage V naught. So as we saw, V naught was nothing but the what? We initially we calculated this node voltage. After that, this node voltage was coming out the same as this average, right? So V1 was H into Vs, right? H1 into Vs plus 0 into H2. And H1 is nothing but the D, average value I am talking about. So you can easily write TVS, right? In last session, I don't think I have solved any buck converter problem. I solved that boost converter problem, and that I utilized that concept of switching function. So we did not need to learn that concept of what will happen of switching after switching at every instance. So any type of circuit you can just apply wherever the multiple switches are connected. Let's say this, why I choose this node, right? So here multiple switches are connected to this node, this switch 1, this switch 2. So I can apply nodal or switching function approach at this node. Afterward, I will move ahead towards the point where we require the value. So that's why here V1 average we calculated easily as a dVs, and D is given in the problem and Vs is also given in the problem. So zero point 0.4 into 50, that will be 20 volt. Okay, it was very easy problem. The second part in this problem is to find the maximum and minimum inductor current. B part is IL max and IL min. Now, how we will calculate this? So again, if you want to calculate current across inductors, you need to know the voltage, voltage equation. VL is equal to L di by dt. Okay. And this waveform I wanted to show. Let me show the waveform. This is a typical waveform of a buck converter. For the period of switch conducting, the voltage across inductor will be Vs minus V naught. Let me take this circuit in parallel. Huh. So when this switch is getting turned on, okay, so this VL voltage is nothing but the Vs minus V naught. Okay? And when this switch is getting turned off and diode is on, this VL is nothing but the V naught, right? Or minus V naught. Okay. VL plus V naught is equal to 0 by KVL. So that will be minus V naught. Okay. And if VL is positive, we know VL is equal to L di by dt. If VL is positive, your di by dt is positive and your slope will be increasing. It means your inductor is getting charged from some value, some minimum value to some maximum value. And during the negative value of voltage, your inductor is getting discharged. Okay, this is very simple thing. And since this capacitor is connected directly across this inductor, so whatever the ripple will have in that inductor, that will try to flow through the capacitor. So whatever the ripple this inductor contains, that will try to flow across this ripple, and whatever this average value, let us say average value, this will try to supply to the load. Okay, so this is basic funda. Here ripple will get ripple will pass through the capacitor, and this load or average inductor current that will pass through the load. Okay, so this is what happening. This ripple we considered in capacitor flowing. Okay, and of course the average value is 0 because all average value is passing through the load, so average is considered as 0. Okay, fine. I hope there is no issue till this point.
Fine, sir.
Yeah, thanks. Now we need to calculate maximum and minimum value of inductor current. So this is nothing but the IL average. So IL max, if I want to know, since this is del IL, so that will be IL average plus del IL by 2. And IL average we know that is I naught. Okay. So I naught we can easily calculate since we have calculated V naught. IL average would be V naught by R, and V naught was 20 divided by R. Some R value must have been given. So R is also 20 ohm, 20 plus del IL by 2. Now the point is here to calculate del IL. Okay. So, let us suppose any instance, either turn on or turn off. So during turn on period, the voltage across inductor was Vs minus V naught, and the change in inductor current is del IL, and this time is 0 to dt. So we will take that time dt, right? So L del IL by dt is equal to dt. Why? Because I am considering due to that we are considering the time for turn on only. Okay. So Vs minus V naught, and from this point we can easily write as Vs minus V naught by L into D. We can write T as a 1 by F. So, because we will be given with switching frequency. Now we know Vs 50, we know V naught 20, we know D, D, F and L, whatever it was given. D is zero point 0.4, F is 20, and L is 400. Okay. 0.4, 20 kilohertz, and F was, sorry, L was 400 micro Henry. So if you calculate this value, you will get something like 0.75 ampere. Okay. Sorry, 1.5 ampere. So we have calculated the value of del IL. We will see what will happen in discontinuous mode. Okay. So after this point, we try to calculate IL max. That was nothing but the IL average plus del IL by 2. IL average was 1 plus 1.5 by 2. So that is nothing but 1.75 ampere. Similarly, IL min we can calculate with the help of IL minus del IL by 2, and that will be 1 minus 0.75 and it will be 0.25. So this inductor current, uh, we will identify it from graph. So it is varying from 0.25 to 1.25, right? No, sorry, 1.75. So 1.5 of peak to peak ripple was present with the average value of 1 ampere. So this was, based on continuous conduction, a straightforward question. Okay. Now we will see what happens in case of discontinuous mode. Okay. So again, I will take the help of a graph from the same book just to explain it. Just observe this graph and what difference you are able to see it. There are one or two differences you can easily identify. First difference is, your this voltage waveform. First, you focus on this voltage waveform. This is getting zero for some period, okay? And any other difference or any other consequence of this point? Yeah, so another point is here inductor current is also becoming zero for some point and it is not getting started with some initial value, okay? So it is starting from zero, it is getting end up on zero and it is still zero for some finite duration. And that is, sometimes not desirable. Um, so and here is what is the value of is, or what kind of waveform is will contain. So is will be nothing but the inductor current during when switch is on. Okay, and when switch is off, it means your diode is on and your source is getting disconnected from the inductor. So that's why your is looking like that. See here, when this switch is disconnected, then your is, it is not flowing anywhere, right? It is getting disconnected from this inductor, hence it is zero here. Okay. So we identified two difference. One is your voltage is getting zero for some finite duration, and your inductor current is getting zero for some finite duration. Okay. So what will happen? Just from intuition, what you can observe? Will it increase the value of IL and VL, or will it decrease the value of IL and VL? What do you say?
Decrease the value of VL. Sorry, yes, sir, VL and IL.
Okay. So if you see here, uh, this negative value is getting chopped off, right? It would have been this much. So if you see V naught was nothing but the DVS in this case. And now if you calculate this negative value is getting reduced. So if you will calculate this area, you know, it will be a bit in on higher side compared to the earlier case. However, my question should have been like what effect will have on V naught, not on VL. Okay. So V naught will be increased due to the fact that this negative portion is getting eliminated. And IL IL is starting itself from 0 and it is again 0 for some point because IL doesn't go in, negative direction. It will always remain in positive direction. Okay. And however, its value is getting reduced and its conduction period is also getting reduced. So IL average will reduce and V naught average will increase. Okay. Now we will see some expressions just to get more familiar with this kind of circuits. So now at this point, if we apply this volt second balance 0 to t 1 by t VL dt is equal to 0, from this expression only we can easily calculate the average value of V naught. Okay, our objective is to calculate average value of V naught. So 1 by t from 0 to dt, the VL value is nothing but the Vs minus V naught dt plus dt to t. Now here, not dt to t because some portion is 0 here. So dt to d plus d1 into t, right? Any doubt till this point? It is getting started from dt and this portion width is d1t. Let me erase this portion. So this point will have the value d plus d1 into t. And the value of inductor voltage is minus V naught into dt, and that will be equated to 0. Now, if you solve this expression, just one step expression, you will get V naught is equal to Vs into d divided by d plus d1. Okay. Earlier, this was 1. Earlier, in continuous conduction mode, d plus d1 was 1. If you would have added the d plus d1, it would come out to be 1. But now in DCM, discontinuous conduction mode, d plus d1 would be less than 1. Okay. You can see it from here. D plus d1 would be less than 1. Okay. Now at critical point for just continuous, if we want it to just sufficient value of inductor which will enable the circuit to operate in just continuous mode, that expression will be d plus d1 is equal to 1. Okay. Now we want to find this d1 value in terms of d so that we can make our life easy. Okay. So for that purpose, we will take again the help of inductor current because we are talking about discontinuity. We are talking about your inductor current discontinuity. So we will take the help of inductor current. I would like to drag this graph of inductor current. Okay. So this graph of inductor current, I keep it in front, and now we will write the value and expression of inductor current. So we want to find out the area. If we will find out this area, then we will be good to go. So initially we will take this half into del IL, because this is nothing but the del IL. And in discontinuous conduction mode, del IL is nothing but the IL max. Agree?
Yes, sir.
Fine. Into dt plus half for this next one, half into del IL into d1 t, and we can divide entire by t. This is how you calculate area, right? Now, if I sum up, I will get half into del IL into d plus d1. Okay. And I can write del IL as IL max, half into IL max into d plus d1. Okay. This is the value of IL. I hope no doubt till this point. After this point, what we can do, we can just equate it to, we know that IL average is I naught. Okay. And we know the slope of this inductor current, this slope. So we can write it half into I max. Here I max is nothing but the, di by dt. If I write, it is nothing but the I max divided by
DT.
dt. Correct. So further, just simplifying it, I should not make it messy. So further, I can write I max is equal to di by dt into dt. And this di by dt we know that is VL by L into dt. So this I max I can write as a VL. Okay. So our further task would be just to equate IL is equal to I naught, and IL we can write now, this value we can now write as a V naught into D1 into T divided by L, because we got in terms of VL, right? VL we can write in terms of D1 or D. During turn off, this value was V naught. So we can write V naught into D1 into T by L, and this D by D1 would come as it is and is equal to V naught by R. Now you must have known that why I wrote in terms of V naught, because I note it in terms of V naught, and I just wanted to make it in terms of V naught so that this both will get cancelled out and we will be left with the equation d1 square plus dd1 minus 2l by rt. Okay, this is the expression, final expression. What we need to do, it may look like there is a lot of effort, but simply we just need to equate this IL average is equal to I naught, which we already know from the circuit, because anyway circuit will be given, or you will be familiar with the circuit. You just equate IL is equal to I naught. You will know the average value of IL in case of discontinuous conduction mode. Okay. And further, if you equate this both equation, you will get this kind of quadratic equation. Now, We have all learned quadratic equations in our school. So after this point, I can write only plus sign, because if we take minus sign, it will of no use because duty ratio will never come in negative. D square plus 8L by RT, B square minus 4AC kind of divided by 2. So this is your expression which we wanted in terms of D. Okay, this is D1. This is the period. This is the period D1T. If you just multiply it with T, you will get in terms of how much duration it will contain for turning off the switch. Okay, so that finite duration D1 in terms of D, and that dependency on only L and R and frequency. So this D1 is function of L, R, F. Okay. Now to make this same circuit in continuous conduction mode, you can either increase the inductance, that is one thing. You can reduce the resistance, or you can increase the frequency. Anything you can do, it will depend on these 3 points only, right? Because you know why I am saying increment in frequency. This T will get in numerator when we convert it in frequency. T is 1 by F. And if you increase this numerator, anyway your D1 will increase. Okay. Again, L is already in numerator, so it will directly affect this value. And R is in denominator, and we all know the higher the value of resistor or load, your current is going to be less. So hence it will make it DCM. So this conclusion we got here. And finally, I would like to write in terms of V naught and Vs in terms of D and D1. So we wrote it like D by D plus D1. And now we can write, we know the value D divided by D plus D1. D1 is nothing but the minus D plus D square plus 8L by RT by 2, and it will further get simplified as Vs into 2D divided by D plus D square plus 8L by RT. So this is your final expression. Okay, because we calculated D1 in terms of D, and whatever the value of D you will get, it will suffice that. Either it is in discontinuous mode or continuous mode, this will be your expression. Important expression. Now, the condition for getting just continuous, or to checking, if you want to check any circuit whether it is in continuous or discontinuous, your D1 plus D must be less than 1. It means your D1 will be always less than 1 minus D. So if you are given with duty ratio, and if you know the expression of duty ratio D1, which was nothing but the minus D plus under root D square plus 8L by RT divided by 2, which is nothing but the expression of your quadratic equation, and you can easily verify the circuit. Okay. So again, we will solve the same problem which we solved earlier, just with a bit tweak in that value. And you might have guessed already where I will do the tweak, or where this author have done. So what are the differences now? Earlier, if I match those values,
Sir, capacitance has no role in continuous mode or discontinuous.
capacitance has role in, to reduce the ripple in voltage, not in your ripple in current. So
Okay.
actually, whatever the ripple in your inductor current, that much ripple of that much ripple of your current that must be passed through that your load capacitor. So it should be just capable of filtering out that ripple. Okay. So what I mean to say, just let me explain it. Just I will take the circuit here. So whatever del IL it is creating or it is getting induced in the circuit, that much del IC, okay, that much current it should filter out. And we all know IC is equal to C dV by dt. Let me show you the waveform of capacitor as well. See here. So whatever this ripple it is present in your inductor, that is getting directly reflected in capacitor, and IC we know that is C dV by dt. Okay. Now dV by dt is nothing but the IC by C. Okay. The more value of capacitor you will have, the less value of dV by dt you will have, and hence this ripple will get reduced. Okay. So this is depending on your capacitor. Okay. But not this inductor ripple. This is voltage ripple, not current ripple. And indirectly, that voltage ripple is getting induced from this current ripple that is getting induced in your inductor. Are you getting confused? Should I clarify it once more?
Yes, sir, got
Got
it.
it, sir.
Oh, got it. Thanks. So yeah, that's what I meant to explain. Whatever ripple is induced in your inductor, that will reflect in your capacitor. And in capacitor, IC is nothing but the C dV by dt. And we know dV by dt is IC by C. So the amount of capacitor you will use, it will affect your ripple in voltage. So, okay. So these are the values here. Now some change in values has been done just to show the effect of discontinuity. And here it is asked, first you need to compute the V naught. Again, let me take the circuit. Oh, this is the circuit here. And in discontinuity, okay, if you want to check whether your circuit is continuous or discontinuous, you just need three things: F, L, R, and of course, if you are trying to find in terms of D, so D must be given. So if you can easily see, let me just zoom it. L is given, F is given, R is given, and D is given. So everything is given here. Now you can easily calculate D1 in terms of D, and that was nothing but your minus D plus D square plus 8L by RT by 2. Okay. And if you will put this value, D is minus 0.4 plus 0.4 square plus 8 into 400 to 10 to the power minus 6 divided by R, that is 20 into T, and t is nothing but 1 by f, and f is 20 into 10 raised to power 3. Okay, divided by 2. Now, if you will calculate it, just a second, I will calculate it, and you will get the value of d1 as 0.29. Okay, you had these three values, you have d, you calculated the value of d1, and now we will verify d plus d1 is what? Either less than 1 or greater than 1. To get in discontinuous, it should be less than 1. D was zero point 0.4, zero point 0.4 plus 0.29. It is 0.69, which is obviously less than 1. It means it is in DCM. Okay. Now, if we know it is in DCM, the question was to find out V naught. Okay. Now, V naught we can write Vs into d by d plus d1. Earlier, if we did not check it, we would have written in terms of simply dvs. We would have written simply dvs. And if you write dvs, you put the value of zero point 0.4 here, you will get a wrong answer and you will lose your marks. So if you have this formula, just check it once and just get confirmed. And generally, this type of problems asked for 2 marks. So you will lose your that 2 marks along with additionally 0.67 of negative. So just try to verify it in your exam. Now we know the value of Vs. Vs is 24 into D, zero point 0.4 divided by 0.4 plus 0.29, and that would come out to be 13.9 volt. Okay. If you would have calculated in manner of dvs, with the help of dvs, d was zero point 0.4 and vs was 24, so that will come out to be 7.2 volt. Okay, so and this kind of option will be surely present in your exam. Okay, 7.2 volt will be definitely there. And one more observation, this 13.9 volt is greater than this value. Okay, so that we verified from this example that in discontinuous conduction mode, your average value of voltage will be higher. Okay.
Yes, sir.
Yeah, fine. So just let me show a graph here, which is again taken from the same book. So this is how your V naught will vary. Okay. During discontinuous mode, it is getting increased. Our zero point 0.4 was the duty ratio, and corresponding to that, this 13.9 value is there. And as we increase the duty ratio, as we are increasing in this side, so at some point, your converter will come in continuous mode. And after that point, you will lose all the issue of your discontinuity. But for that thing, I already told that D1 will depend on F, L, and R. So either you have to higher L, lower R, higher F. So that will be cost for this continuous mode. So this happens if you increase your duty ratio, the charging time of inductor will increase. And further, if your charging time is very high, let us see this point is zero point 0.8. So if you are charging it for zero point 0.8 of your time period, 80% of your time period, then your discharging can't be complete in 20%. In general case, it can happen in certain exceptions. So that was it for discontinuous buck converter. I hope you would have got it. If any doubt in this, I am still here. And I will show you one problem which was directly asked on this formula in GATE some 2003 or 2, I don't know. So they asked like this is the chopper circuit. Just read it for a bit. I am providing the options what they given. So these are the options here, and they just asked like what will be the value of D in terms of whatever the parameters are given in this problem to get the converter at the boundary of continuous and discontinuous conduction. Okay. So if you know this concept, you can easily write D plus D1 is equal to 1. And we have already calculated D1 in terms of D. So I will just write D1 again so that you will get familiar with this expression. So D1 is minus D plus D square plus 8L by RT by 2. Okay. Now you just need to plug in this value in this. Okay. Just plug in here. So you will get D plus minus D plus D square plus 8L by RT by 2 is equal to 1. And now you just need to equate this equation and you will get 1 minus D is equal to 2L by RT. If you solve this expression, which I guess is not that much tough, one or two step I am skipping here just for the time. And you can write here D is equal to 1 minus 2L by RT, and which was present in the option 1 minus 2L by RT. Okay. So this was, I guess, get 2002 problem. If you go and see, you will find this problem in your previous year questions. Now, I will take one very easy problem based on your inductor current. So this was question again asked in some get 2003. It is shown that whatever you are asking that this del IL and del IC, the relationship between both. So they have already checked this concept in past. So they indirectly said that del IC is 1.6 ampere peak to peak. They said that this current is 1.6 peak to peak. Okay. And they given the value of I naught, which was 5 ampere, and they asked to find out the peak current in switch S. So we need to find out the value of switch current. Okay. Now, firstly, we have to infer if del IC is given, it means ripple is given, and that ripple is coming in capacitor from inductor, and this del IL is nothing but your del IL is 1.6 ampere. Okay. Now, this switch will get on only for that time, whatever the duty cycle is assigned to that switch. And whenever this switch will be on, okay, this this inductor and capacitor and load will be connected to the switch. So whatever I already saw, let me again bring back that circuit and graphs.
Sir, 6.6.
6.6, you did silly mistake. You are correct. Your approach is correct, but you did a bit silly mistake. Why you think till I solve this problem? So just let me bring that graph here. Is I shown, I guess that I is this one. So you see, whatever the peak of IL, that will be the same in source current. Why? Because inductor is directly connected to this switch and source when the switch is on. So indirectly they are asking IS peak is nothing but the IL peak. Okay. And we know that IL peak is nothing but the IL average plus del IL by 2. Okay. Now you might have guessed where you committed the mistake. So
Yes, sir.
yeah, correct. So I note they already provided 5 ampere and we were given with del IC that is 1.6 and this by 2 and this will be 5.8 ampere. Okay. So you just not forget to divide it by 2 and I hope this is all. So any doubt in this problem or in entire session because it's time to now wind up the session. Okay, then if no doubt is there, then we can wind it up.
Thank you, sir.
Yeah, thank you.